Okay, so I'm going to be talking about the power of locality for network algorithms. This is joint work with Christian, who is here. There are various projects in here, but all of it is with Christian, with Mickey Brotbar, who is just finishing up at UPenn this year. One of the pieces of work is with Sanjeev Khanna, who is at UPenn. A couple of the pieces of work are with Brendan Lucier, who is actually an undergraduate here, and he is a Waterloo native. He grew up in Waterloo. And one of the pieces of work is with Xianghua Teng, who is at USC. Okay, so online networks are often massive. So, for example, the World Wide Web has trillions of static websites. Facebook has over 1 billion users now, so these are some representations of these. So there are questions that we can ask about these networks. Some of the kinds of questions that people like to ask are, for example, what is the ranking of pages or the ranking of sites on something like the World Wide Web? So something like PageRank. There are many questions that have to do with what is the most influential site. So the most highly connected site, for example, or the most influential site under a certain model, like the KKT, that's the Kempe Kleinberg-Tardosh model. People also ask things like, can you cover the graph via local moves, so a dominating set problem? How can you find a dominating set? This is like a recruiter problem on LinkedIn. Okay, you want to go from your network to be able to cover the whole graph within, in the closure of the neighborhood. Okay, so there are certain constraints one has. Sometimes the network is only visible in small steps, so you can only see 1 or 2 hops from where you are, like on Facebook. And Facebook and LinkedIn and these other sites change what their rules are over time, but you can just see friends of friends, but not how many friends they have on Facebook. On LinkedIn, you can see friends of friends and how many friends they have, but you can't see anything about them unless you pay extra. Okay? There are also limitations on the time to compute something, which is very relevant if you have a really massive graph like the World Wide Web. Okay? So in the first case, you need a local, in general, a local approximation algorithm, because I can't do anything global. I can't see globally. I don't know what the network structure is except 1 or 2 hops from where I am. And in the second case, even though you might be able to see more, it turns out often that if you want a fast running time, a local algorithm will give you a much better running time than a more global algorithm. You may have to give up on how well you tend to approximate the answer, but you sometimes can trade these things off with a local algorithm. Okay, so the outline of this talk is, first I will talk about things that have local access constraints. Okay, so I'll tell you what I mean by a local information algorithm. I'll tell you some of the things that we can do on a preferential attachment graph, and I'll also tell you some of the things that we can do on a general graph, on a general network. Okay? So the second part of the talk, and this is actually switched from what I said in the abstract, the first and the second are switched with each other. You don't have a local access constraint, but you may be trying to get a really fast algorithm, like a sublinear algorithm. If these graphs are massive enough, then our definition of what fast is not the typical theoretical computer science definition that exponential is long and polynomial is fast. Even linear is no longer good if you're talking about 1 trillion sites. So we're trying to get sublinear algorithms without an a priori access constraint. And I'll talk about 2 problems. One is the PageRank problem. Okay, so how do we compute what pages have significant PageRank really quickly? And the other is looking at the independent cascade model, which is also known as the KKT model. And there I want to find the most influential nodes, for example, for viral marketing. And again, I want to do it really, really fast. Okay, so I'm thinking of a very large network, and I want to identify what is a seed set such that if I give them all Windows 8 phones, it's going to spread over the network really fast. Okay, so a networking problem with local access constraints. So somebody comes to a new town, they want to meet the most influential people. So there's some network there. So what we view this as is, can we find the highest degree vertex? Okay? So how do we do that? Well, when I'm looking at this, it isn't hard. If I knew all the degrees of the nodes, that's easy. But what if I knew nothing and I just, met one person and saw that person's friend and then went out from there? I went out greedily because, well, here, what I did was I actually looked at that person's 2 friends, and then I looked at that person's friends, and then what I'm going to do here is I see that that person is actually the most highly connected person. Okay? So how well can a graph algorithm perform when it has only local visibility of the network structure? On natural networks, like a preferential attachment network, and as a function of the level of visibility, okay? And so here, online social networks can differ in what is visible. So as of the time these slides were prepared at least, and maybe again now, this is what you could see in Facebook. You could see, so here you are, here are your friends, and you can see their friends, okay? On LinkedIn, you could also see how many friends their friends had. Okay, not who they were, but how many. And on Orkut and Google+, you could see even more than that, okay? So what is the impact of the design choice? You may think local, it can't make a really big difference. If you're seeing 2 hops, if you're seeing 3 hops, if you're, if I'm seeing my friends, but not how many friends they have, can that really, can there be a big difference from this to that? And it turns out that for certain problems, we can show that there is a big difference. Okay, so more generally, the kinds of problems you might want to look at here with local access constraints are things like search problems. So I want to find the highest degree node, the most central node, something like that. A coverage problem, so the minimum dominating set, maximum K coverage. A connectivity problem, if I'm given 2 points, can I find the shortest path? Or given a point and I want to multicast out to something else, can I find the fewest edges to go along to multicast? And I'm going to look at this in cases where the graph topology is seen locally as we build an output set, okay? So step by step as we build an output set. Okay, so what is some related work? Ronit Rubenfeld, so that's the R here and there, and some other people like Nogalan is one of these people, have been coming up with sublinear algorithms. So Ranit has this new program of trying to find sublinear algorithms for property testing, for example. And so they're trying to make a local decision at each vertex which is consistent with some global solution. Okay, and that's like a new, big research area for her. Okay, Brotbauer and Kearns, Michael Kearns, in 2010 gave a sublinear time local approximation algorithm in the cases in which you could either jump or crawl out from a certain site. Their goal there was to estimate a quantity, for example, the maximum number of neighbors, and the trade-off was a runtime versus the approximation. We're actually later in the talk going to see some improvements of what they found. Okay, and then Kleinberg in 2000 looked at navigating a small world. So he was inspired by the Milgram experiment, the 6 degrees of separation. There was a model of this, a small worlds model. It's the Watson-Strogatz model. Agents can find, and so what Kleinberg was doing was not just looking at the Watson-Strogatz model, but trying to see how you would navigate in that model. And he was finding ways that agents could find shortest paths via local routing, but he did have some global information about the network. So we're not going to have any global information about the network in what we're doing here. Okay, so part one, which is the one where we have imposed local access constraints. Okay, we're not imposing this on ourselves to get a faster algorithm, but it's imposed by the way the information is revealed, like if you're a recruiter trying to expand your network on LinkedIn. So I'll give you a general model of what we call local information algorithms. Then we'll look at how these act in the preferential attachment model, what we can do with a local information algorithm in the preferential attachment model. And then we'll look at the minimum dominating set problem, which is, trying to find a set such that the set plus all of its neighbors will cover the space for a general network in the case of a very local algorithm. Okay, so the input is that I have a graph, which I don't know anything about, and I want to output a subset of the vertices. For example, I might want to find a feasible S, like find a set of edges which connects these 2 points. It either does or it doesn't. If it does, it's a feasible solution. And I want to do it such that I'm minimizing the size. Okay, so what I'm going to let myself do are 2 operations. I'm going to allow myself to add a random node, or I'm going to allow myself to add a node which is visible from where I am, so which is on the boundary of my set S. And the visible region is all nodes which are, let's say, at distance less than or equal to R from S, plus the induced subgraph. Okay, so plus all the edges that are internal. I'm going to call this an R local algorithm, and I'm also going to ask that I know how many neighbors the outermost nodes have. Okay, so it's one local. If I look out from my existing set, distance of 1, see my existing set, the induced graph out at distance 1, plus how many neighbors all the sites on the boundary have. Okay, and to map this into like questions on Facebook and LinkedIn, you should think of the distance as the distance from your current set, so out from your friends, okay? So it's not just you, it's you and whoever your friends are, and a one local algorithm looks at distance 1 out from them, plus the induced graph, plus the number of neighbors of the set of the sites on the outside. So a one local algorithm would look something like this. It'd just keep building. Okay, it might jump over there. A 2 local algorithm is a much bigger chunk, okay? Although you might think, could this really make a big difference? Okay, so this talk I'm going to focus mainly on 1 local algorithms. And one of the interesting things is that at least a lot of the time with the rules that they have, actually after we came out with the work, Facebook changed their rules. I'm not sure if there was a correlation there, but Facebook, you couldn't do a 1 local search out from it because you didn't know the number of neighbors of your neighbors, of the neighbors of your friends. And in LinkedIn, you could do what we're calling a 1 local search. Okay, so an example would be ST connectivity. So I'm given 2 vertices, S and T, and I want to connect, I want to give you a connected subgraph which contains S and T. So here's an example of something that is problematic. Okay, optimally it should be of order R, but if I look at a local algorithm, what would a local algorithm do? Well, a local algorithm doesn't see that central thing that's covered up, okay? This is R+1, so it doesn't see that. So what I do then is I choose this node. Once I choose that node, I know that there's a path that goes across here, okay? I mean, it could be that this one is connected to this one, but that's not going to help me get across. I pick another node down here, and now I know that it's not there, and so on. And I've got to go through essentially everything. I've got to go through N over R nodes until I find the path. So it's actually, you know, I actually have to look at a lot there. Okay, so now you know what the general question is. I want to go out slowly, and I want to ask, you know, how long will it take me to find certain things up to some approximation? Okay, so first I'm going to look specifically at preferential attachment networks, since a lot of things seem to be roughly approximated by preferential attachment networks. So the preferential attachment model, Barabashi and Albert in '99, and then Bolobash and Reardon in 2000. I mean, Barabashi and Albert defined it, Bolobash, Reardon proved a lot of things about it. So you begin with a small fixed graph. Each new node connects to, let's say, m greater than or equal to 2 previous nodes at random, and proportionally to how many neighbors they currently have. Probability that it connects, as I said, is proportional to the number of neighbors it currently has. Okay, so what are the properties of this? It's connected with high probability. It has small diameter, so for m greater than or equal to 2, the diameter is log n over log n, so it's a pretty small diameter graph. It doesn't take you a lot to hop from any site to any other site. It has power law degree distribution, so the probability that I have k neighbors goes like 1 over k cubed, which we consider to be slow relative to things like, you know, the random graph, which is e to the minus k. And older nodes tend to have a larger number of neighbors. It goes like square root of n over the time of birth, or square root of when the site was born. Okay, so finding the root. So what I want to do is I want to find a set that contains the original node. Okay? So an opportunistic algorithm would initialize the set S to an arbitrary node, and I'm thinking, I can get rid of this later, but I'm thinking for now that I can recognize if it contains the node, the original node. If S does not contain the original node, then it's just greedy. I look around, I pick the neighbor that has the largest number of neighbors, okay? With a 1 local algorithm, I can see my neighbors and how many neighbors I have. I pick the one with the largest number of neighbors. Okay, so it's 1 local. Okay, and as I said, it's possible to remove the assumption that the algorithm can figure out what is the node 1. Okay, so the theorem says that an opportunistic algorithm, one local algorithm, can find node 1 in a very short amount of time, very sublinear, log to the 4th power, with high probability over the random graph process, over this preferential attachment process. Whereas a random walk, by contrast, would require square root of n. So it's much, much faster, okay? Which, you know, when you begin to think of billions or trillions of sites, is really going to make a difference, okay? So LinkedIn, if I'm looking for the root there, it's going to take of order log to the 4th power. Whereas Facebook, I'm going to have to land up doing something like a random walk. It turns out to take square root of n. Okay, and if I know how to do that, which I'll tell you roughly the proof of that in a moment, but if I know how to do that, turns out that I can also do ST connectivity in the same amount of time by just connecting S and T both to the node 1, and I can connect K terminals in order K times log to the 4th, okay? So, you know, so I take the original node and I connect them to each other, to all of the nodes that I want to connect. Or I can find K nodes of largest degree in a similar amount of time, log to the 4th n plus K. Find the first node, but don't stop the algorithm. So here's the basis of the proof. Whoops, that shouldn't, well, okay, anyway. Log to the 4th n is what that should be, okay. So after K star polylog iterations, the hope is that you would reach a node of size 2 to the K, you know, in this preferential attachment process. I keep going out, you know, and I look over size K, over you know, radius of size 1, and now I pick the one that's biggest there, and I look out from there, another one, and I keep going out. And you would hope that after K polylog iterations, the algorithm would reach this node. The problem with this is that reaching a node of high degree does not necessarily imply progress. And here's an example. So what happens is that let's say that I'm going to start over here, and I'm going to greedily go along, and I'm trying to find this guy, okay? And if I'm greedy, I'm going to get stuck, because what happens is these guys get filled in, but then there's a bottleneck. Then, if I'm looking greedily, I really should be going here, okay? But this is going to look like it's a better node for me to choose, okay? So I would return this set, and that wouldn't be what I want to do. However, the observation, it's a kind of obvious observation, is that if there were a path to the original node in which everything was of degree greater than D, then I would never choose anything of degree less than D, because I would just be going along that path, and greedy says I keep going along this, you know, greater than D path. Okay, so the question is, how many paths like this can I find? Okay, so how common are these good paths? Okay, well, it turns out, and that symbol hides a little ugliness, okay? It's a pretty symbol to hide ugliness. For any, and any is not quite any, but you know, most nodes and most parents, the degree of the parent is bigger than the degree of the node over some garbage that we can estimate with a probability which happens to be greater than 8/15. The important thing about 8/15 is that it's bigger than a half, okay? M is bigger than 2, so that means when this site comes in, it actually has 2 parents, because it, remember, as the sites come in, they kind of, they attach to their parents, right? And a site comes in and it attaches to 2 existing sites, so 2 older sites. So for m greater than or equal to 2, each node has at least 2 parents, each of which is good with probability greater than 1/2. And so we get a supercritical branching process, so we actually can get to node 1 along paths of this sort. Okay? I'm shoving some things under the rug just to tell you what I've shoved under the rug, but I'm not going to take it out from under the rug. I'm just going to leave it there. But if you see it there, know that I know it's there and I can clean it up. There's too much dependency between the nodes, okay? So once a node appears in one good path, what I'm going to do is I'm going to never allow myself to use it again so that I won't have dependency in my estimates. Turns out I can get away with doing that, okay? There are so many good nodes around that I don't have to reuse it. And the argument really does break down close to the root. You may end up having to query a lot more nodes close to the root, but that's okay because there are not that many nodes close to the root. So those are kind of the 2 dead things under the rug, and we did take them out and bury them, okay? So, okay, so that's the crux of that proof. And as I said, that one actually allows you to do ST connectivity and some other things. That was on preferential attachment graphs. Now I'm going to look at a problem on a general graph. What I want to do is I want to find the minimum dominating set. So a dominating set, once again, is a set such that if I look at that set plus all of its neighbors, I cover the entire graph. Okay? And this is what a recruiter, really ambitious recruiter, wants to do when they look at LinkedIn. They say, I want to have so many connections that I'm always just 1 hop away from the person I might want to find, okay? So in this example, those 2 green nodes are enough to cover the entire graph, okay? I mean, with them and their neighbors. Okay, so what I want to do is I want to find the smallest set such that this is true. A lower bound using set cover says that it goes like the log of the maximum degree of the graph. And in fact, with a 3-local algorithm in 98, Guha and the guy in Maryland. What?
Katz? Jonathan Katz?
Not Jonathan Katz. Yes, yes. Semi-cooler. In 1998 showed they were trying to get it as local as they possibly could because I don't think in 98 they were thinking of severe access constraints. They were, you know, but they were able with a 3-local algorithm to match the lower bound, okay, to get something that's scaled like log of the max degree. And so the question is, how well can we do with a 1-local algorithm? Okay. So a greedy algorithm, what I do is I initialize S to a random node. If I haven't covered the whole thing, then I want to add a node from my neighboring set which maximizes the set and the extra node and the boundary of that, the D of that, okay? Okay. So what is the problem with this? Well, let's just look at what happens in this case. The optimal is very fast, but let's see what a greedy algorithm does. This is a graph which is cooked up to, you know, pay back somebody who's greedy, okay? So you pick that node and you say, okay, well, what am I going to do? Now, obviously, I'm going to add that, you know, really juicy node there. So I do that. Okay, well now I could go here or I could go here. Well, whoops, what if or there. So what if I go there and what if I go there and what if I go there and, you know, and then I eventually get that other one and I go over. So a greedy algorithm could take a really long time if I'm unlucky on this graph, okay? So that's not good. So what's wrong with this? So what's wrong with it is that I'm being too greedy, and I'm not even wondering at it all and looking at anything else, okay? I'm not letting myself see that there might be something else nice out there. So instead, what I want to do is a greedy random algorithm. So I'm going to initialize S again to a random node. If I haven't covered the whole set, then I'm going to add a node that maximizes, just as I did before. I'm going to do a greedy step, but I'm also going to do, after that, I'm going to do a random step. So I'm going to take the neighborhood of that V, delete the dominating set, and I'm going to add that. I'm going to take some random site in there. That would have helped me in the last case, because then I would have picked a neighbor, one of the ones I was in, and then I would have been near the really high degree node. And it turns out that the greedy random algorithm gets a 1 plus 2 log delta, 1 plus 2 log delta, where delta is the maximum degree approximation. So pretty good, almost as good as the other approximation in expectation and with high probability. So the crux of this is what I want to do is I want to look at a V which is in the optimal solution. So I want to look at some site which is in the optimal solution, and I want to show that the algorithm doesn't take too long to cover that V. And I have to cover everything which is in the optimal solution, so I want to know that I don't take too long to cover it. Okay, so what I'm going to do is I'm going to consider some X which is chosen greedily by the algorithm and which covers some neighbor of V, okay? Now there are a couple of possibilities. Either V was visible, okay? So what happened here was that I was at this site, I saw V, now I had already covered a lot of other sites, actually. And I also saw X. Well, if it turns out that this is the case, then it must have been that X must have covered many nodes itself, or else I would have, if V were visible when I chose X, then it must be the case that X had lots of neighbors that were not revealed yet. So choosing X was a good idea. Okay, so that's not so bad. Now, what if V was not visible? Okay, there are two possibilities. Either the same as before, X had tons of neighbors, so it was still a good idea, or X did not have tons of neighbors. Well, if X didn't have tons of neighbors, then in the next step, I'm supposed to choose a neighbor of X. X does not have a lot of neighbors, so so I'm going to pick like 1 over the number of neighbors. So here with probability 1 over the number of unexposed neighbors. So here with probability 1/4, I'm going to pick this guy. Well, then V will be exposed in the next step. Okay, and so it doesn't take too long. Either X by itself was a good choice, or if X was not a great choice, well, then with reasonable odds, I'm going to still expose V very soon. And this is not a proof, but you can build a proof out of this, charging certain amounts and stuff. So this is the basis of a proof. Okay, so this is how you can build this minimum dominating set, okay? And using that minimum dominating set, you can, in a very short amount of time, cover the graph for something like Facebook, for something like LinkedIn, whereas you can't do it for something like Facebook. Okay, so the conclusions for this first part, which has to do with having local access constraints. So here, it's not my choice. It's not that I'm trying to get a sublinear algorithm. It's just that I have local access constraints. We define these local information algorithms, which involve sequential decisions with limited network visibility. We see that many problems can be solved locally and very efficiently in preferential attachment networks, and some in general graphs, and the level of visibility can have a strong impact on the approximation ratio of the problem. I mean, a surprising impact, really. Okay, so these are things where I have a limitation on that it has to be local network access. Now, let's say that I don't have a limitation, but I do have a limitation on running time. Okay, I don't have infinite compute time available to me. I'm the Bing search engine and I want to rank my sites, or, you know, I'm a viral marketer and I want to go on Facebook and figure out pretty quickly, you know, to whom I should give low-cost iPads or Windows 8 phones or whatever. So what do I do there, and can I use Locality to get much more efficient algorithms? Okay, so first, PageRank. So probably most of you know this, but to do PageRank, which is kind of the lowest order approximation that is done in any of the ranking engines, they do something like this, and then they put about, you know, 500 hacks on top of it. But you take the World Wide Web as a digraph. You have your sites are the web pages, your edges are the hyperlinks. And then what you do is that you do a random walk on the web graph. Every 1/alpha step, so, you know, 1/7 of the time, I don't follow a link out, but I skip to a uniformly random site. I keep doing this until I get the stationary distribution. The relative weight of that page in the stationary distribution is the page rank of that page. Okay, so more precisely, I have a random walk matrix M, which is the adjacency matrix properly normalized. So AUV is the adjacency matrix of the directed graph, okay? And I normalize by 1 over the number of paths that I have out from U. And the stationary distribution is the vector pi, okay? So this is if I'm not restarting at all, okay? The problem with not restarting is you can often get stuck, okay? You know, I post a paper on my web page, the paper has no outlinks in it, I walk there and I'm stuck, okay? I was just telling you about PageRank where you restart randomly. Let's say I always choose to restart at the homepage of CNN, okay? So now I have a random walk with a restart at the homepage of CNN, okay? So in each step I do one random walk step with probability 1 minus alpha, and I jump to the CNN homepage with probability alpha. Okay? And so now I have some other matrix, not just the random walk matrix, but I have alpha times this thing, which brings me back to the CNN homepage, plus 1 minus alpha times this, and so the stationary distribution of that is this vector pi u, which turns out to be what's called the personalized page rank. Let's say I took these vectors, these pi u's, and they're rows, okay? They're like row vectors. Let's say I stacked them on top of each other for every page of the entire web, okay? Then I would get something that I call the PageRank matrix, PUV, where what I'm doing is I'm restarting at U and looking at the contribution to V, looking at how much it's going to contribute to the stationary distribution at V if I'm restarting at U. So as I said, this pi U up here, and it's the same thing down here, just written differently, is called the personalized PageRank vector. This is personalized to the CNN homepage. Always restart at the CNN homepage. Those are the rows of the PageRank matrix. The columns of the PageRank matrix are what are called the contribution vectors, okay? Those are how much each site is contributing to the page rank of V. So if I go along the bottom and I pick the MSNBC homepage, I can ask, how much does Christian Borg's homepage contribute to the MSNBC homepage? How much does Chayes' homepage contribute? How much does the CNN homepage contribute to the MSNBC homepage? Okay, those are the columns. If I sum the column, that gives me the page rank of V. So if I sum the contribution vector of V, that gives me the page rank of V. So it's summing all possible personalized page ranks into V. Okay, so if I did my restarts at a particular page, and I'm going to sum that for doing my page ranks, my restarts at any particular page, then I'm going to get the page rank. So the page rank itself is a row vector which kind of lies under the bottom of the page rank matrix, and it's just the sum of all the rows. By the way, the columns themselves each sum to 1. Okay, so this is a nice matrix. Okay, so what I want to do is I want to compute PageRank, but I'm going to look at what's called the significant PageRank problem. So all that I want to know is I want to know, I've got some number delta, and I want to know all pages. I want to find all pages with PageRank bigger than delta, and I could have some that have PageRank less than delta in there. I just better have everything with PageRank bigger than delta, and I don't want to have anything with PageRank less than delta over 2. Okay? So I want all things with significant PageRank in there. Okay? So there have been a lot of people have worked on this problem, because actually you don't just want to find the PageRank of everything. You usually want to find the pages with significant PageRank. So there was stuff going back to 2003, something called the power iteration method, that gave you of order the number of edges. Okay, in a sparse graph that's n, but in a dense graph that's n squared. There was a linear algebra improvement of that, which gave you of order n, even in a dense graph. There's also a lower bound on the running time of n over delta. This basically comes from the example, if you consider an example in which you have roughly n over delta sites, each of which have PageRank delta, and all other sites have PageRank 0, then you're going to need at least this much time to find them. So the question is, can we use locality? Can we come up with a local algorithm which gets to within an additive epsilon approximation of the lower bound? Okay, so that gets to within some additive approximation of the lower bound very fast, like, you know, I want the lower bound maybe with some extra logs in there, but that's it. Okay, I can't do much better than that, but, you know, can I get a good approximation to this very quickly? So what do we have to do if we're trying to compute this? Okay, what I have to do is I have to calculate each PUV. Okay, so I have to calculate each of these things, which are, you know, how much Christian contributes to CNN's homepage. Okay, so Christian is U and CNN is V there. Then when I get that for Christian and Shy and MSNBC and everything, then I'm going to want to take that and I'm going to sum that column, okay, to get the page rank of the site V. Now I've got the page rank of the site CNN, okay, but there are a lot of other sites. So I have to do that for all n points, and a priori each one of these should be taking of order time n at least, right? So this looks bad. Okay, so I'm going to try to do each one of these and not lose too much. So I want to do a local calculation of an epsilon approximation to how much Christian's homepage contributes to the CNN homepage. Okay, so previous results, a lot of people worked on this. There were deterministic approximations. Jen Whittam and Anderson et al. So Jen Whittam got of order 1 over epsilon. It's an additive epsilon approximation. The first one had a log n in there. Anderson et al. Using backwards random walks, which is going to be, and going back to like the Spielman-Teng stuff and using backwards random walks, got rid of that log n. These still both involve the maximum in degree, okay, which is fine, except if the maximum in degree is unbounded. If the in degree is unbounded, then I don't want the maximum in degree in there, okay. But then you say, well, come on, you know, let me just do something random so that I don't end up hitting this thing with a really high in degree. Okay, so Fogaras et al. In 2005 did a Monte Carlo-based approach in which they removed the dependence on the maximum in degree. They gave a multiplicative rather than an additive error. And the bigger problem there was that, I mean, this wasn't a problem for what they were trying to do, but it depended on the particular matrix element. And so what we did was, and it was based on terminating random walks, which we're going to use also. So we did a modification of what they did. We handled the concentration better to remove the dependence here. So a terminating random walk, so when you look at a lot of these kinds of problems, what you find in Anderson et al., some work we later did with John Hopcroft based on Anderson et al. And the Spielman-Teng stuff, and then the Fogaras et al., you try to look at things coming in backwards. You try to think of the flows into things backwards. So a terminating random walk is a random walk which terminates with probability alpha, and with probability 1 minus alpha moves to a random outlink, a uniformly random outlink. So our algorithm says, for a while, here we're trying to get additive epsilon multiplicative rho approximation. You run a new terminating random walk up to a certain length, okay? If the walk terminates before reaching that length, then you look at the last site that it visited before it terminated, and you give that site a point. You say, okay, well, that site must have been pretty important, okay? And you look over all the counting here. You output the average count that's accumulated at each node. If you go through all of this, it turns out you get a running time, which for our purposes, the important thing about this running time is that it's like 1 over epsilon. So we're getting an additive approximation on this matrix element with a running time which scales like 1 over epsilon, where epsilon is the additive approximation. Okay. It's not yet clear why that's good, but it's going to turn out that that's good. Okay, so let's say we've figured out all we want to about the matrix elements, okay? Now what I want to think about doing is I want to think about taking all the significant enough matrix elements and adding them up to get the page rank of the site. Looking at, you know, Christian's homepage contribution and the New York Times homepage contribution and everything to the CNN webpage. Okay, I can't just sum these all up, okay, because it would take time in just to sum them all up. So what do you do when you can't sum and you want to save time? You sample, and you hope that you sampled enough that the average is going to be close to the right thing, okay? So what I'm going to do is I'm going to pick L points. So I don't pick Christian, but I pick the New York Times, and I pick Chayes, and I pick L of these points, and I'm going to add them up. I'm going to add up L contributions to the CNN homepage, to the page rank of the CNN homepage. Add up the contributions of links in from Chayes' homepage to the New York Times homepage. So L over N is what fraction of the sites I've chosen, okay, just by random sampling. And I want to know if the whole thing should be bigger than delta, but I've only picked L over N of them, so I should compare to what you know, if they were right on with the average and I was looking to see whether it was bigger than delta or not, I would want to look at these numbers and compare them to delta L over N. Okay, it turns out that does not work. Okay, however, something somewhat more sophisticated, well, okay, so let me tell you why that does not work. To make sure that the error doesn't drown out the expectation, I need to take epsilon of a certain size, so not too much additive error, okay? But I also need, I mean, look, if I sample one number, what's wrong with sampling one number? Well, what's wrong with sampling one number is that you're gonna have a lot of variance, right? So I'm gonna do a Chernoff bound, okay? I've gotta get my variance tight enough, okay? So L has to be big enough that it's reasonable to sample, and Chernoff is going to tell me when that's the case. So it turns out that I need L roughly of order n over delta. So now I have L terms, each of which has an additive error of you know, this 1 over epsilon. So it comes out that I get the square of what my lower bound was, okay? The plus logs or times logs, okay? So this naive sampling doesn't work, okay? So what I'm going to do instead, and I'm not going to go into it except to say that this kind of thing works sometimes, okay, is I'm going to choose a lot of scales. So I'm going to choose epsilon t to be 2 to the minus t, okay? I'm going to choose lots of scales. And I'm going to estimate how many of the entries contributing to the CNN homepage PageRank lie in the interval between epsilon t and 2 epsilon t, okay? So, you know, in this little interval. And it turns out that if I land up making estimates like that, then I'm going to spend most of my time on estimates of the larger p's, because I've got these things, these intervals expanding at an exponential rate, okay? And that is going to turn out, with lots of work, to be enough to estimate whether this is bigger than delta in the running time that I want. So sampling wasn't a bad idea. I just can't do it naively by choosing L of them. And that's something for you to remember, that sometimes you can't add. When you want sublinear, you can't add. You have to sample. It's something you see in Rubenfeld's work all the time now. You have to sample, okay? But naive sampling doesn't work because you're spending as much time on the things you were going to care about as on the things you're not going to care about. So you do it on multi-scale, you're concentrating your effort where you're going to care about it. Okay, and then finally, I can do this for one, but whoops, I have n sites that I want to look at the PageRank. Well, it turns out that if I think about combining all of this together, most things I'm not going to care about. Most contributions I'm not going to care about. If I think of something that I don't care about, almost like a 0 in the matrix, it turns out that I can use sparse matrix methods to do all n columns in parallel, and I can maintain the running time that I want, okay? So, you know, it was first for a given estimate, the locality feeding back in with terminating random walks. Second, for a column, sample, but sample intelligently, sampling more where it's going to be bigger. And third, do everything in parallel, and that's really sparse matrix methods. So locality, multi-scale analysis, sparse matrix methods leads to a running time which essentially matches the lower bound to find an approximation of all nodes with significant PageRank. And if I now take this delta to be order n to the p, so, you know, let's say I want everything with PageRank bigger than 3rd root of n, okay, then I'm going to get a running time which is n to the 2/3. So I'm going to get something sublinear, okay? So this is, and, you know, I might have to take this even bigger to get this small enough if n is a trillion. Okay, so that's how we get sublinear in that case. So something that's a priori totally different and technically totally different than in spirit. There are some similarities. Sublinear algorithms for models of influence maximization. And again, we're going to see locality not being imposed from the outside, but being imposed if we want to be able to get a sublinear algorithm. So there's the independent cascade model, which was introduced as a model of viral marketing. I think Richardson had done it even earlier than KKT. So I have an oriented graph, n sites, m edges, and I have weights along the sites, and the weights are the odds that if I, if there's an edge from Shy to Christian, the odds that if I give Shy an iPad, Christian will buy an iPad, okay? And I want to look at the random size of the set that's eventually infected starting from a given seed, okay? And for fixed, so I then want to fix the number of seeds that I'm gonna market to, and I want to find the choice of the seed so that I get the maximum possible expected influence. Okay? So, previous results, well, it turns out that this expectation is submodular, and as many of you have probably heard, when things are submodular, you can often get 1 minus 1 over e approximations. Whenever you see 1 minus 1 over e, just ask, what's submodular? And someone will think you know what you're talking about, okay? And you can do this with a greedy algorithm. You don't even have to be very sophisticated. Okay, now with Oracle access, it turns out that to this number itself, this has a running time of k times n, the number of seeds times the size of the network. But now I have to simulate this because I don't have Oracle access, so that's going to add a factor of the number of edges and poly in 1 over epsilon. Okay? But if I look at this, m is at least of order n, even in a sparse graph, m is of order n. And so this is at least quadratic in n. If I'm trying to go to Facebook, quadratic in a billion is not good. Okay, so what am I going to do? Well, we get 2 results. One is a nearly linear time algorithm. So if I just lose relative to that 1 minus 1 over e, a little epsilon, we were able to get time, which is m plus n instead of m times n times poly in 1 over epsilon. And we also found, we constructed an example with a lower bound like this, so this is essentially optimal. And we also got a sublinear time algorithm with a worse approximation. So instead of this constant factor, I got a 1 over beta factor in a time which scaled like n itself over beta times the arboricity of the graph. Arboricity is the number of spanning trees you need to cover all the edges of the graph. The important thing to realize is for many social graphs, the arboricity is essentially finite. It's planar. For a planar graph or a preferential attachment graph, it's essentially finite. And again, if I take beta to be like n to the p, I get something sublinear in n. Okay, so just a couple of pages on the key elements of the proof, and then we're done. So the key idea here is so again, you see random sampling. Okay, so it's to pre-process the graph with random sampling. We come up with a sparse hypergraph representation of the graph, which maintains a lot of information about the high influence nodes. And each hypergraph edge is going to represent the set of nodes which were influenced by a particular node in the transpose of the graph. This transpose of the graph is not unrelated to the fact that we were looking, or like in the Anderson thing, that you were looking at backwards random walks and stuff. You're looking at the things which feed into something. The degree of the set S, which is my seed set in the hypergraph, is roughly proportional to the influence of S in the graph. And it allows us to get an estimate of the marginal influence very efficiently because basically the things that are important get repeated. And this backwards, this transpose gives us that. Okay, it's local and it's applicable in many access models. You're only doing basically jumps and crawls, so crawl out or a jump to a random edge. And finally, in the sublinear variant, we have two possible seed sets. One we get using a greedy algorithm according to the constructed hypergraph, but the other, and this is not in principle, unlike what you saw in that earlier proof, the other is a singleton that's selected at random according to the hypergraph degree distribution in this hypergraph representation. So instead of just being greedy, you alternate greedy with random. Here it's in a different representation, but it's just when you're not probing the space well enough, don't be greedy, be random. Okay? So the conclusions are local network algorithms may either be absolutely required because there are local information access constraints, or they may just be desirable due to increased runtime efficiency. The recurring elements in these algorithms are sampling, sometimes at multiple scales, rather than trying to probe all elements. I mean, you're not going to be sublinear if you probe everything. Interspersing greedy steps with random steps to see more of the space, not to get stuck in the wrong part of the space. And maintaining locality even when it's not imposed on you by using backwards random walks, transposes of matrices, these terminating random walks to find the large contributors and not to be re-estimating the significant things in many steps. And with these methods, it's possible to get sublinear time algorithms with reasonable approximation ratios for many questions of interest, like finding the most highly connected nodes, finding the connections between nodes, covering the network, which a recruiter would do on LinkedIn, trying to find the significant PageRank pages, trying to find the sets of maximum influence. So the types of questions that one would like to ask, we are finding methods to get those in sublinear time, which is what we really need for algorithms that we're going to try to use in practice. Okay. Absolutely. And as you can see, a little more information means a ton less privacy. Okay? The other way of interpreting these results is to say that if I give you what seems to be an innocuously larger amount of information, it's not innocuous. You can use it to cover the graph. Okay? And we're hearing about stuff in the news where a little bit of information and people just uncover all kinds of things, right? So you can flip this around and say that although the designers, and I don't think the designers realize this actually, okay, but if they slightly change the amount of information, it may expose a lot of private information.